Hello, everyone. Thank you, Dominique, for your introduction. Today, I will present a part of my doctoral work on the non-destructive diagnosis of marble sculpture by coupling 3D imaging with acoustic tomography. The object studied in this work is this altar of Apollo. It is made of Carrara marble. It dates from the late 1st century before Christ, and it was located in the Roman theatre of Arles at the base of its pulpitum, which is the small wall in front of the scene. We could work on this altar thanks to the Museum of Ancient Arles and thanks to its curator, Alain Charon. On this altar, on the front side, the god Apollo is represented. And on the lateral side, the execution of Marsyas is represented. It was sentenced to be skinned alive after claiming he was a better musician than Apollo. On the right side, you can see Marsyas hanging by a tree from his hand, waiting for his execution. And on the left side of the altar, you can see the executioner who is sharpening his knife. The issues on this altar was first to evaluate the internal state of cohesion of the marble. And secondly, the museum had a more precise question about the crack on the right side of the altar. It wanted to know if this crack was going through the entire height of the altar, as for now they never move this object because they are not sure that it could bear it. To try to answer this question, we perform acoustic tomography on this object. For that, the principle is to define a network of emitters, noted E, and receivers, noted R, on the object, and to make ultrasonic waves propagate across the sculpture. The important requirement to acquire enough data is that the network of emitters and receivers allowed to cover the maximum volume of the object and that the paths of the ultrasound in the object cross each other. The important parameter that interests us is to measure is the ultrasonic pulse velocity, so the velocity of propagation of the ultrasound in the object. What we measure directly during the experiment is the time of flight of the ultrasound between each emitter and receiver. So we have then to measure the distance between them. The problem on this kind of object is that the geometry is generally quite complex, and direct measurement, distance measurement with tape measures or compass are relatively difficult to carry out. To remedy this problem, we use a photogrammetric 3D model provided by the museum, on which we place each emitter and each receiver. And on these models, they are directly associated with their 3D coordinates. Therefore, it is easy to calculate distances when we have those coordinates. The experimental setup was the following. Here you can see the time of flight measuring instruments that we use with 54 kilohertz transducers. Then to locate directly during the experiment the position of the receiver on the front side and the lateral side of the altar, we projected directly the 3D model onto the side of the object. So on the picture's position are marked with the kind of pink circles. For the back of the altar, we couldn't project any model on it because of the wall behind it. So we use a tracing film to locate the position of the emitter, and we place them afterwards on the 3D model. We use the 38 position for the emitter and 36 for the receivers, and we had a total of 560 measurements of pulse velocity. This is the histogram of the velocity in the altar. The average pulse velocity is about 3,000 meters per second, which corresponds to a rather good state of conservation for marble. This is a more special representation of this pulse velocity. Each emitter and receiver are linked with a colored line. The color depends on the value of pulse velocity that was measured between them. And they are divided in 3 categories based on the damage classes that were defined in the 90s for marble. And therefore, the yellow-green lines correspond to an increasingly porous marble compared to a fresh marble. The orange line corresponds to a marble exhibiting granular disintegration, and the red lines correspond to a fragile marble. The good news is that the red line represents a quite small minority out of the total measurement made on the altar. So it seems to be in rather good condition. However, instead of those global ultrasonic pulse velocities between each emitter and each receiver, we would rather have a 3D imaging of the velocity inside the object to then be able to have those kind of cartographies by slicing plans in the object. To do that, we reconstructed the velocities inside the altar by using an inversion with SIRT algorithm, SIRT for simultaneous iterative reconstruction techniques. I'm going to present the matrix system on which we apply this inversion. For this step, we had to artificially divide the object in smaller cubic cells represented in 2D on the schematics. And if we look at one emitter receiver pair, the total time of flight of ultrasound between them that we measure can be rewrite as the sum of the travel time in each cell by the ray. We can transform this equation to make distance and velocity appears. The distance traveled by the ray in each cell of the object and the velocity in the cell. The distance can be calculated quite directly. So then only the velocities at each position are missing. If we do that on all emitters receiver pairs, we get this matrix system in which we know the vector for the global time of flight and in which we can calculate the distance, the travel distance. And then we apply a CIRT algorithm to invert the system to calculate the vector with the inverse velocities. In the end, we can have this kind of cartography. So this is a slice plane, which is shown by the plane is shown by the line on the picture. So on this cartography, the blank areas are areas in which we didn't have enough data to reconstruct the velocities. What can be noticed is that the value of velocities at the back of the altar, so on the right side, are lower than the one on the at the front of the altar. This pattern is found on most slice in the lateral parts of the altar. So in this part, the back could be generally weaker than the front of the altar. However, when we look to numerous slices in the altar, especially in the view shown on the picture, we can't really detect the cracks that the museum was interested in the slide. So either this technique is generally not adequate for this kind of issues, or our measurement around the cracks were not dense enough to get this kind of information, or the crack was too superficial considering the network of emitter and receiver that we use. Therefore, thanks to a 3D photogrammetric model that gives us the external geometry of the altar, and combined with the measurement campaign of ultrasonic pulse velocity, we could get a 3D imaging of the velocity inside the altar, which give us information about the internal state of the sculpture. This technique is non-destructive for the object, and it can display some zone of weakness in the altar. However, we could not during our experiment identify some cracks that were visible from the outside. Perspective of this work is to consider curved ray tracing when we reconstruct velocity instead of the straight one that we use here. To also do the same kind of imaging with signal attenuation, and could bring other information about the state of the object. More long-term perspective to make this experiment contactless by using lasers in emission of the wave and also in reception, and also to combine this kind of work with the numerical simulation of the process of degradation that could be at stake. Thank you very much for your attention.